Hello, everyone. We are Team Acumentrics bringing you the third edition of the FaultLine project. This is a continuation of FaultLine 2021. Our technical directors are Brendan Smirbeck, our lead director, Bill Owens, the overseer of the project, and Najib Ashak, machine learning consultant. Our team consists of two computer engineers. First is Matt McAdams. Second is me, Sean Maglione. Acumentrics, located in Walpole, Massachusetts, was first founded in 1994. They specialize in rugged, uninterruptible power supplies. Today, they offer products for power conditioning, surge and blowout protection, as well as seamless automatic power backups. The project motivation starts with power consumption analysis. By analyzing the power signatures coming in from the device, we can do what is called predictive maintenance. This is when you analyze those power signatures to categorize them and also detect faults. This drastically reduces the likelihood of a catastrophic failure because the device fault can be identified prior to this failure. The end goal is a power supply that is able to recognize faulty devices before they cause problems. The best anticipated outcome of this project can be broken down into four parts. Firstly, is to expand the scope of the general models to include additional devices. Secondly, we want to improve the accuracy of these models. This is done through optimization and better data sets. Next, we want to implement on-device training. This utilizes the Jetson Nano as a computing platform in order to train a new device with a new model for fault detection. Lastly, we want to demonstrate transfer learning. This is the idea of having a specialized model that can be transferred to new devices. The economic impact for the company is an uninterruptible, fault-tolerant, self-diagnosing power supply. While Acumetrics already possess uninterruptible power supplies, the addition of the fault detection technology could provide a product that is able to detect faults in devices and report them as a warning before they cause catastrophic failure. Our first key technical accomplishment started with developing a new virtual environment for running project code. Next, we improved data acquisition. Specifically, we introduced a faster sampling rate as well as more detailed data sets. We also expanded the general model to include a secondary device, as well as improving the accuracy of this general model. The first device, which was started by FaultLine 2021, was the wind machine floor fan. We introduced the Dirt Devil and Duralite bagless vacuum cleaner into the general model. Power signatures are the cornerstone of this project, as they provide the information that our machine learning models need to perform fault detection. A power signature is essentially a set of data points of the power usage of a device. Power signatures can represent a device at a given state. Identical devices operating at the same state will end up having similar power signatures. In the case of FaultLine, we're focusing on simple electromechanical devices. This is because they are easy to replicate similar power signatures, they recognize demonstrable faults, and they also have a strong potential for transfer learning, which is the on-device training aspect of this project. We accomplish recording power signatures through the Acumentrics SmartPDU and our computing platform, which is the NVIDIA Jetson Nano. When a device is plugged into the SmartPDU, the Nano is able to read the power signatures and export them as either a file or, in the case of on-device training, directly to the model. The circular buffer is an essential part of on-device training. It allows for the seamless transfer of data without having to store that data in any other place. The data is transferred to this buffer, which is then overflowed once it is full. I also improved the general model through better data. I did this by refining data collection and analysis. Specifically, I designed and implemented a master data file to compile and organize all of the data collected. I also implemented a number of data quality control measures, which allowed for cleaner and better data sets. Wow, I need to redo this. I improved the general models through better data. I did this by refining data collection and analysis. I first designed and implemented a master data file to compile and organize data. Next, I implemented a set of data quality control measures as well as automating procedures to clean up the data once it's been collected. I also added a number of new parameters to the data, which will aid in the general models. This includes physical location, timestamp, and port number. Over the next month, I want to continue to automate data collection processes. Next, I want to deploy the inference stack with the on-device model. This is used for the on-device training part of the project. Next, I want to demonstrate fault prediction. This is the part of the project where the SmartPDU is physically recognizing faults for both fans and vacuum cleaners. Lastly, I want to be able to finalize these models, including the on-device models, and be able to demonstrate the transfer learning capabilities. I'm going to pass this on to Matt, who will explain machine learning.
Thank you, Sean. I'm Matt McAdams. Now, using machine learning, we plan to take all of our collected data and transform it into a model, which can determine the device that's plugged in, the functionality, and the fault state, if faulty. This works by creating a virtual set of neurons, similar to the way a human brain is put together. We can set up as many neurons in as many layers as we want, but finding the right configuration is crucial to getting the best results. In the input layer, you have the incoming data, the power signatures we collected, the locations from which they were collected, and any other information we can think of. Through training, the model determines which inputs are more important, adjusting the weights of each connection until it has a pretty good idea of what the incoming information means for the outputs. Then the output layer contains as many outputs as there are possible outcomes to the problem. In our case, one layer for each fault state, depending on the device. To better train these models for the individual scenarios, we plan to implement transfer learning. What that means is we'll take the output layer off of the model completely, freeze the lower layers. This way the model can continue to learn and specialize itself to the equipment it'll be working with, while maintaining its general shape and ability to determine the outcomes. Now, we decided pretty quickly that we were going to need to set up a new working environment, since the image of the Jetson Nano that we were given from last year unfortunately couldn't keep up with the new demands of the project. From there, we rated different electromechanical devices based on the important criteria, as Sean mentioned earlier, to determine the best fit for the project. We then decided on parameters to collect along with the power data from devices. From that point on, I spent most of my time adjusting parameters such as how many layers and nodes to use, what the training cycle looked like, and so on. And from there, I can continue to train the model and find the most accurate one. In January, I plan to begin designing a new model for on-device training. Taking the general model we've put together and implementing transfer learning, as I've described, we can use the Jetson Nano to train the local model as it's collecting data. Manipulating and adjusting this and the general model will consume my attention for the remainder of this project, working as hard as I can with Sean to find the best possible models for fault detection. We are very confident that we can meet each of our future goals, which will lead us towards the best anticipated outcome, designing a new model for the personalization and customization of the connected devices, get some more data, always need more data for machine learning, and demonstrating real-time inference on the SmartPDU using the model. Now, when taking all of this into account, we are considering several risks to achieving our goal. In the event of a pandemic infection, we're preparing a second hardware setup so Sean and I can continue this project remotely. We've considered solutions for each of these possible obstacles, including damage to the Nano, insufficient data, hardware acquisition issues, communication issues, compatibility issues. We've got solutions for everything. And finally, we'd like to thank Brendan Smurbeck for his dedication to leading us to success, Bill Owens for his oversight, Najeeb Shak for his crucial insight on machine learning, and most of all, Dr. Harish Sunak for his dedication to his students and this program, and for ensuring our success in the program and in the future.